A derivative is the instantaneous rate of change of a function. Now, the average rate of change between 2 points is simple. It's written as the change in y divided by the change in x. This means if we wanted to find the average rate of change between, say, points 3, 4, and 5, 7, all you have to do is find the change in y, which is 7 minus 4, and divide it by the change in x, which is 5 minus 3. This would yield 3 over 2. However, the average rate of change doesn't tell us about the change of a function at any particular point in time, only over the given interval from 3 to 5. This means that if we had a function that looked like this, although the average rate of change between these 2 points, let's call them a and b, might be 0, because our delta y is 0, it's not reflective of the behavior of the function at every point during this range, because clearly the function is changing at values. Furthermore, when we plug in this formula for an instant for one particular point, we're going to get 0 over 0, which is indeterminate. This gives us no information about the actual rate of change. So for this reason, we use limits when we're computing instantaneous rates of change. Let's go over the limit definition of a derivative. Now, we're going to start with the average rate of change between these 2 points. But instead of labeling them at values a and b, I'm going to label them at values x and x plus a small change in x. That means this space right here is delta x. So the average rate of change formula will say that we have to find the difference in y values divided by the difference in x values. So that'll be f of x plus delta x, which is this value here, minus f of x, this value here, divided by the change, which is simply delta x. Now this is where limits come in, because as this point slowly moves closer and closer, the rate of change is going to get more accurate to that solely at x. And what you find is that if you take the limit of this function, this rate of change function, as your delta x approaches 0, that actually becomes the instantaneous rate of change. And this is the limit definition of a derivative. Now that we have this limit definition of a derivative, let's find some derivatives. For instance, let's look at the derivative for the function 3x squared at x equals 2. So first, let's find f of x. So 3 times 4, it's just 12. And then f plus delta x will be 3 times 2 plus delta x whole squared. And delta x, remember, because it's in the limit, we don't have a value for it, but it approaches 0. So let's write out the form. It becomes 2 plus delta x whole squared minus 12 all divided by delta x. Once again, this is the limit as delta x approaches 0 of this entire thing. Now let's expand this. So we get 3 times, now when you expand something a plus b whole squared, you get a squared plus 2ab plus b squared minus 12 over delta x. And now immediately you can see here, this 3 times 4 is going to cancel out with this negative 12. So what we're going to be left with when we expand it is going to be 12 delta x plus delta x squared over delta x. And we can cross out a delta x from everything. So we're going to cross out the square, we're going to cross this out, and we're going to cross this out, and that equals 12. So that means at the point 2, 12, the rate of change of this function is equal to 12. Or essentially, this function will have a slope of positive 12 at this point. Here's one thing that's really important to note though. When we look at this derivative, we're never plugging anything in for delta x. It's always approaching 0. So really, what we're doing in a derivative is we plug in a certain value x, you do some operations to it, and you get a result. So really, the derivative of a function is another function, and we can prove this by plugging in some functions into this form, just not using specific points. Let's start with the really simple function of y is equal to 3x. So here's our function y is equal to 3x, and all we have to do is remember our limit definition and plug it in. So f prime of x, with this being regular f of x, remember f prime simply means the derivative of, is equal to the limit as delta x approaches 0 of 3x plus delta x, because remember it's just f of x plus a small change, minus 3 times x, which is our original f of x, all over delta x. Once again, you can see this 3x and this minus 3x are going to cancel out. So all we're left with is 3 times delta x over delta x. Once again, crosses out, and we're left with a final answer of 3. This means that for every point along the function y is equal to 3x, the derivative, or the instantaneous rate of change, is just going to be equal to 3. And this makes sense intuitively, because if you look at not just y equals 3x, but any linear line, the slope between any 2 points is always going to be the same. There's never any change in the rate of change. And so we can say the derivative of a linear function is going to be constant, because the slope never changes. Let's go back to the other function we had, which was y is equal to 3x squared, and compute the limit definition of a derivative and see what the function says. Here's the function f of x is equal to 3x squared, and once again, all we have to do is plug it in. So instead of x, we're simply going to have x plus delta x, and it's still going to be squared, minus 3x squared all over delta x. Let's expand and simplify this. It's going to be 3 times x squared plus 2x delta x plus delta x squared minus 3x squared all over delta x. We're going to use similar patterns. We see this negative 3x squared will cancel out with the 3x squared. So what we're going to be left with is 3 times 2x delta x from this and this, plus 3 delta x squared all over delta x. Once again, we can cancel out one term of delta x, and we're going to be left with 3 times 2x, which I'm just going to simplify as 6x, if it'll let me. 6x plus 3 delta x over 1. And because, remember, throughout this whole thing, what we're actually evaluating here is not the function, but a limit as delta x approaches 0. As delta x approaches 0, because we have this term over here is going to approach 0. So we can cancel it out, which leaves our final answer as 6x. And remember, when we calculated it initially by plugging in the point, we said the derivative at x equals 2 was 12. And if we plug that in, we simply get 6 times 2 is equal to 12. So this result is the correct derivative of 3x squared. Now, you might have noticed a pattern with these derivatives. The derivative of the function 3x, which is an x to the 1, became 3, which is x to the 0, because that's just a constant. The derivative of the quadratic function, 3x squared, became 6x, which is an x to the 1 function. And this is an actual pattern. If you have a polynomial function of x to the n, the derivative is going to be a function with the degree x to the n minus 1. Specifically, the derivative of a function x to the n is equal to n times x to the n minus 1. And here's how you prove that. Let's say we have a function x to the n and we want to find the derivative. So this is f of x. And now all we have to do is once again take the limit. So f prime of x is equal to the limit as delta x approaches 0 of x plus delta x to the n minus x to the n over delta x. And you have to remember, when you're expanding powers like this, you have to remember that the coefficients also change. So when you look at something like Pascal's triangle, which is a way to help you, it goes like that. It goes 1, 2, 1, 1, 3, 3, 1. So the point here is that the first coefficient is always going to be 1, and because this is 0, 1, 2, 3, third degree, the second coefficient is always going to be the degree number. So essentially, the second coefficient is going to be n. So when we expand x plus delta x to the n, we're going to start with x to the n times 1 plus x to the n minus 1 times delta x to the 1 times, remember, our coefficient is just going to be n. Plus, then we're going to get a lot more terms, and it's going to end, remember, because it's always symmetrical, with another coefficient of n. This time it's going to be x to the 1 and delta x to the n minus 1 plus 1 times delta x to the n. We have a minus x to the n here, so that's going to cancel out with that. So all we're left with is this huge expression divided by delta x. Now, because every term in here has a delta x in it, this was the only term that didn't, and it got canceled out. We can cancel out the delta x. So this is gone, and this n minus 1 becomes an n minus 2, this n becomes an n minus 1, but the specifics no longer matter, because look at what we have now. If we were to rewrite it, just to make it cleaner, it's the limit as delta x approaches 0. Right now what we have is n times x to the n minus 1, there's no delta x, plus a bunch of terms that all have delta x in them. So if it's the limit as delta x approaches 0, every single thing that's being multiplied by delta x is just going to go to 0. So all this cancels out to 0, which means this limit is equal to n times x to the n minus 1. And this is the derivative. This is f prime of x, where the function is x to the n. Let's write our new rule down. This is called power rule. If f of x is of the form x to the n, then f prime of x is equal to n times x to the n minus 1. And this works for all sorts of exponents. So if I had x squared, that would turn into 2x to the 1. If I had x to the 5.5, its derivative would become 5.5 times x to the 4.5. So not only does this work with fractional or rational exponents, it also works with negative exponents. So imagine if I had x to the negative 1/2, its derivative becomes negative 1/2 times x to the negative 1/2 minus 1 is negative 3/2. So the power rule works for not just polynomials, but all powers of x. Now, before we go into all the rules of differentiation, let's really quickly look at a visual representation of derivatives. So first, let's draw a curve. The rate of change between 2 points can be drawn as a secant line, which means it passes through 2 points. That's a bad secant line. There we go. So the slope of this line represents the rate of change between these 2 points. But remember, a derivative is instantaneous, and that means it's the rate of change at only 1 point. So instead of it being the secant line, it would actually be the tangent line to the function at only that point. Remember, tangent means it only intersects the function at this specific point. So, in its most simple form, the derivative is the slope of the tangent line. But we know that this is just a derivative at a point, but the derivative of one function can be another function. So let's graph those two. Now let's imagine our function was like this. This is a basic quadratic parabola. Then we know our function would be linear. Assuming this was just x squared, our derivative by our power rule becomes 2x to the 1. Now let's compare between the derivative and the function. When x is negative, the derivative is negative, which is this line right here. Now remember, derivative means rate of change, and so that means the rate of change of f of x is negative. So let's write this. If f prime of x is negative, then rate of change of regular f of x is negative. And a negative rate of change means the function is decreasing. And when we look at the graph, we can see that to be true, because wherever x is less than 0, our parabola is decreasing. It's starting at a higher value and it's ending up in a lower value. Now, the opposite is also true. Wherever f prime of x is greater than 0, it's a positive number, because this line, which is f prime of x, is positive. That means our parabola, wherever f prime is positive, is increasing in value, meaning it starts at a lower number and increases to a higher one. Now here is a very special point, because our derivative, our f prime of x, switches. It's a negative over here and it's a positive over here. It's equal to 0 and it switches from negative to positive. This means the rate of change of f of x also switches from negative to positive. So it starts out decreasing and it switches to increasing. And as we can see in the function over here, it means we have a turning point. So this information is really useful to know because it's good to look at the derivative and from that be able to determine the behavior of the function or vice versa. Let's go over some basic rules of differentiation. So here are the most obvious ones that we've already discussed. If there's a constant, constants don't change, so your rate of change is always going to be 0. If your function is y is equal to ax and it's a linear line, then your derivative is just going to be a, because the slope of the line, or the rate of change, never changes. If you have a polynomial function, or any function that's in the form x to the n, remember there's the power rule that we went over, it's just n times x to the n minus 1. There's another rule where if your function f of x is equal to c, some constant, times some other constant, then f prime of x is just equal to c g prime of x. So all that says is that if you have a constant in a function, you don't have to do anything special with it. You can just multiply it with the derivative. Next, here's the first special case that you have to memorize. If your function is the natural log of x, then your derivative, your f prime of x, is equal to 1 over x. And this is kind of the one exception to the power rule. Since 1 over x is the same as x to the negative 1, if you wanted to come to this result using power rule, your original function would have had to be technically x to the 0, which is a constant. And it doesn't make sense to say that the rate of change of a constant is 1 over x. So, because you cannot get this result using power rule, it is the derivative of the natural log of x. Next, for any log function, so if f of x is equal to log, not just log e, but log base a of x, remember, you use the change of base formula to say this is equal to ln x over ln a, and remember, ln a is nothing but a constant. So with that idea, it'd be 1 over x times 1 over ln a. So 1 over x ln a is the derivative of any logarithmic function. Now, the inverse of log functions, exponentials, are similarly easy. So if my function is f of x is equal to a to the x, my derivative is equal to ax ln a. Once again, there's a natural log. Using this, if my function is equal to e to the x, remember, ln e is just equal to 1, so the derivative is simply e to the x times 1. This is a very special case where the derivative of the function is the exact same as the function itself. Okay, using these basic rules, let's look at some functions. So if our function is y is equal to 4 to the x, our derivative would be 4 to the x ln 4. If our function was y is equal to 2 to the negative x, remember the multiplicative rule of exponents, where this is equal to 2 to the negative 1 to the x, and therefore is equal to 1/2 to the x. And the derivative of 1/2 to the x is 1/2 to the x times ln of 1/2. If you wanted to rewrite this in terms of 2, you could. It would still be 2 to the negative x times the negative natural log of 2. Now, for trig functions, all you really need to know are the most basic functions. So, if your function is sine of x, its derivative is equal to cos of x, which intuitively makes sense because let's look at a sine graph. It starts at the origin, it makes a full cycle like that, and now let's look at a cosine graph, which starts at the peak, goes all the way down, ends once again at the peak. When our sine function has a turning point, it switches from increasing to decreasing. So its derivative switches from positive to negative. And the same thing happens at the second turning point over here, where we switch from decreasing to increasing. Our derivative switches once again from negative to positive. So the derivative of sine x is cosine x. Now let's use the same process to figure out the derivative of cosine x. This time let's draw our cosine function, which starts at the peak, dips down, and ends at the peak. And let's see what its derivative would behave like. It starts off with a flat tangent line, so its derivative should start at 0. Then the function decreases up until this point here. So it should be negative until this point where it's 0 again. It's negative, it becomes 0, and from this point onwards, it's positive until it reaches a third 0 point. And the thing about this blue curve that we just drew here is that this is actually the curve of y is equal to negative sine x. And therefore, if our function is cos x, our derivative of that is equal to negative sine x, and not just regular sine x.